All right, hey everybody. I'm just going to go ahead and get right at this. We are starting our digital learning, and I want to make sure that we're prepared for it. So we've got one last topic that I want to kind of get out to you guys, and that is on logistic growth. And so we're going to cover that now. I'm going to do that by talking about the things that you need to know for the AP exam, working with some examples, and I'm also going to relate things to our current crisis in America with the coronavirus that we've seen. So just sit back and kind of maybe take some notes along the way, and let me know if you are having trouble with any of this material, and I'd be happy to try to come back and help you guys. All right, so what we're going to talk about today is we're going to talk about logistic growth. So this is a BC topic. It is on the exam, even in this new updated exam for this year, these special circumstances. So this is something that you need to know. It normally shows up in the differential equation section along with maybe Euler's method or separable differential equations, maybe slope fields. So all those things that were AB topics, that is where this can kind of end up. So here we go. This is the part that you need to make sure you recognize. So if you kind of look over here on your on this slide, you can see that right here, this part right here is the form of a logistic equation. And you might remember that we had a different type of equation that we looked at where dy dt was equal to ky, and this was for exponential growth. And we got that by separating our variables, right? 1 over y dy equals k dt, integrating both sides, giving the natural log of the absolute value of y is equal to kt plus c. Then we exponentiated both sides and made sure that we were dealing with the correct side. If our y's were always positive, then we get y is equal to e to the kt plus c. And then that e to the kt plus c can be e to the kt e to the c, which can just be some constant I'm going to call r, right? So we could be rect. So that was our exponential growth. This was something that was a topic earlier in the year, okay? But this right here, this is our format for logistic growth, and I want to make sure that you're ready for dealing with this. And to do that, it's mostly about recognizing this thing. So another way it is sometimes written is dy dt is equal to, and what they'll do is they'll factor out this L. So it'll be k ly times 1 over y minus L. This is another really common way to do this. And I want you to know this because this L, this L down here is a very important number. This L is called the carrying capacity. So some of you have seen logistic growth before, especially if you've taken AP biology. It is the S-curve from biology. It's how disease spreads. It's how rumors are spread. It's also about how populations oftentimes grow because things can't grow exponentially forever. Eventually we reach some sort of carrying capacity. Things are eventually going to slow down. So what we do is we start off with this part right here where we are growing exponentially. And then after we've kind of been growing faster and faster and faster and faster, eventually what's going to happen is resources or something in the environment is going to keep the rate from growing at the same amount, and we'll start seeing a decreased rate. So this is what logistic growth looks like. What we do is as we get close, as we head out towards infinity, we approach this line L. In real life, sometimes depending on what the thing is, if it's a population of, let's say, deer or something, you might go above that carrying capacity and then back down. But basically, as time goes on, you're going to try to remain fairly close to the carrying capacity. And there's some extra points we're going to want to make sure we talk about. There's a point here where the slope is the fastest. We're going to talk about that point. We're also going to notice that this thing starts off concave up, and then eventually it turns concave down. And as we go way out here, we are going to become flat. So we're actually going to end up being very linear in nature, and our slope is going to get pretty close to 0. So let's look at our kind of important points to deal with. The solution to our equation is this. I would memorize this. If you don't memorize it, then you're going to have to actually derive it if you need it. And to do that is going to mean that when you come back to this original equation back here and you think about separating your variables, you're going to end up with something on the left side with 2 different y's in the denominator that are factored. And if those of you remember, that means it's going to turn into integration by partial fraction decomposition. So that's kind of a pretty advanced little technique. Alright, so that is something that you're just going to want to kind of memorize. That C is some constant, and then here's the K and the L and the T from before. There's that same L, that carrying capacity. The limit of this thing as time goes to infinity is L. That's correct. I mean, as we go out towards infinity, we're going to approach our carrying capacity, the maximum thing that this system can withstand. And we talked about how the concavity is going to go towards 0. Basically, it's going to be not concave up or down. It's going to become linear in nature. Okay, so when are we at our maximum? When is this rate? When are we at its fastest rate? Well, it's at a maximum when the function gets to half its carrying capacity, when the population gets to half of its maximum. So that's another important thing that you're going to want to kind of hold on to. Okay, so I kind of wanted to divert from how I would normally do things next. And if we were in class right now, I like to play a little game I like to call Zombie Apocalypse, where we all get assigned a number, and we basically see who gets the zombie virus and who becomes the last person on Earth, or at least the last person in our class. And that's kind of a fun game, but we're not in school, and we've got a very serious crisis going on in the world, and I want to kind of pull in some real data points here. So these are the numbers of COVID-19 cases that happened in both South Korea and China. And you can kind of see that both of them are hitting that S-curve. South Korea's numbers are a little bit cleaner than China's. Of course, we might have some reason to doubt China's numbers. There are reports that those numbers aren't accurate. You can see this very fast uptick and then almost an immediate slowing of rate, which is a little unusual. But if you look at South Korea's, you can see that it did start to get exponential, right? We did start to see this rate kind of increase here, right? But then as eventually that rate has started to decrease. Now, I will say that instead of them getting closer to a flat line, right, like something a little flatter, we are kind of still increasing at a relatively linear rate. This is what that flattening of the curve can kind of begin to look like if you do it really well. So South Korea's numbers, if they had continued going up, I mean, they could have already been at this point way earlier. And likely by flattening the curve out, they have saved themselves tens of thousands of people from getting this virus and becoming ill. So in China's numbers, again, a very quick increase, increasing faster and faster and faster, going up bigger and bigger, and then a slowing rate. This is what a logistic curve looks like. Now, I want to take this idea of what it looks like when things start to get better. As you can see, the rates start to decrease. The number of cases per day is lessening. And I want to take that and apply it to what's happening actually right here in our own state. So these are these are the rates of in Alabama as of a couple days ago. I didn't add in yesterday's numbers or today's numbers since they're incomplete. And you can kind of see that we got our first case on March the 12th. And you can kind of see that this was pretty steady and slow for the first little while. We cracked 100 cases on the 20th, and then things started to pick up faster and faster as we started to get testing done actually in our state. And again, even our numbers aren't completely accurate. These aren't all of the COVID-19 cases in Alabama. These are the COVID-19 cases that we have been able to verify through tests that have been reported by the Alabama Department of Public Health. So what I mean to say is there are many more people that have likely gotten this virus in this state that don't show up in these numbers. They either had it and were never tested and now they're better, or they are waiting on tests, or we're waiting on results. So or those results may have never been actually reported to the Alabama Department of Public Health. Most places are here, but if they'd gone somewhere else to get tested, to like a neighboring state, or used some sort of private organization that wasn't cooperating well with the ADPH at the time, then those numbers might not show up here. But you can see that these numbers are increasing faster and faster and faster. In fact, the date that they decided that we were going to stay out of school the rest of the year was somewhere right along in here, and maybe right before that. I think it was the 29th actually, but it could have been just before that. Oops. What I want you to understand by that is that when they made this decision, just a few days ago, we were under 1,000 cases, and we have topped. I know we topped 1,600 yesterday. We're likely over 1,700 now today. We're at a point where we went from 1,000 cases to 1,600 cases, nearly 1,600 cases in a matter of 3 days. And so we can say with pretty good certainty that our state government made a good decision for us to stay out of school, at least mathematically, made a good decision to stay out of school, because we are still seeing an increase in cases per day. In fact, this day right here, where it went from below 1,300 to above 1,500, was I think like something like 250 or 270 cases in one day. So, while these aren't consistent numbers, you can see that some days are larger jumps than others. If you kind of look at them all together, you can see that we are still on a pretty fast increase. We haven't begun the slowdown phase that China and South Korea have seen. And so this just kind of gives you an idea of where we are, both in the crisis, but also how to visualize what logistic growth looks like using real data. So anyway, there's a pretty good website out there. If you look up, I don't know much about them overall, but the alreporter.com, www.alreporter.com, they have a mapping coronavirus in Alabama graph that you can pull up that they are updating with some regularity, that shows you the cases by day. It shows you the total number of cases by day and the increase in cases by day, and also the number of deaths that have been reported in Alabama by day, so that you can kind of keep track of this yourself if you'd like to on your own. Okay, so let's leave this crisis and let's go into something that's I think we can all probably agree more fun, and that is doing some calculus. So here we have the differential equation. So we're given a look. They even tell me this isn't a real AP question. So shout out to Stacy McMullen for the note card. This is a logistic differential equation. They actually say the word logistic. It is a real AP question from a past exam, and that logistic differential equation is given by this form. Well, this form is neither one of the two forms that we have already seen in here. We've seen two different ways of writing a logistic differential equation. One of them was dui dt is equal to ky times L minus Y. The other one was when we factored out the L. Okay, Ly, and then a 1 minus Y over L. This is doesn't have this number factored all the way out, and I can't say that 2 is necessarily my L, because there's a number underneath P. It's not just P by itself. So this is neither of those two forms. How can I get it into those forms? Well, I can factor out that 2. So what I'm going to do is I'm going to factor the 2 out, and what that is going to tell me is that dP dt is 2p times 1 minus p over 10,000. This tells me that my L is 10,000. That's my carrying capacity. So when they ask me this phrase right here, this question, what is the limit as t approaches infinity of p of t? I know that as time goes on, that this particular system is going to reach its carrying capacity. So in that case, I know that that limit is actually equal to 10,000. Okay, so now let's talk about rumor spreading. So this is not an AP question, but it's another pretty decent problem. I can see that this is, in fact, in the correct format, at least one of the formats. It is dy dt is equal to 2y times 1 minus y. So they have factored that thing out, and it's just a 1. So this is y over L. So what is my, so this is my L in this case is 1. So that's a proportion. It's y is the portion of the population that has heard the rumor at time t. So L is 1, and that tells me that the maximum number of people, the carrying capacity for this rumor, is 100% of the population, or which we're referring to as 1. So what portion of the population has heard it when it's spreading the fastest? That's when dy dt is at its max. And we talked about how we know that things are spreading the fastest when we're at half of our carrying capacity. That's going to be when y is equal to 1/2. Okay. How is this going to look on a free response question? I think that's always a question you should ask yourself, because if you're not getting that answer, then the AP exam can be a scary, scary place. So we want to look at this thing and see what kinds of things they can have. One of these is going to be from 2004. The other one's going to be from 2006. We're going to look at them, we're going to work through them, and then we're going to see how they were scored. Okay, so first problem. We have this population modeled by a function p satisfies the logistic differential equation. So here's my logistic differential equation. They call it a logistic differential equation. They did not have to do that, but it is very kind of them to do that, because now I'm looking for very specific things. Now let's see what they ask me. The first question they ask me is if P0 is 3, it means if my initial condition is 3, what's the limit of this thing as P of t, as t goes to infinity of P of t? And then they ask me if the initial condition was 20, what's the limit as this thing goes to infinity? Well, first thing I need to figure out is what is my carrying capacity, because I know that as time goes on, this function is going to get closer and closer and closer to its carrying capacity, right? So we're going to be coming up, we're going to be starting low, we're going to be coming up, and we're going to be approaching that carrying capacity as we head on. So I need to figure that out. So and I look at this, I see this has got the 1 in the front, right here, it's got that 1. So that means 12 is the carrying capacity. And if 12 is the carrying capacity, then the limit is this thing goes to infinity would be 12, and it doesn't matter if I start out above or below. Both of them are going to end up being 12. They're both going to eventually get really, really close to its carrying capacity as 12. Either we'll be removing things from the function, or we'll be adding things to it. So then now they give me another problem. If the initial condition is 3, so if we use that first initial condition, when is this thing growing the fastest? For what value of p is the population growing the fastest? And we learned that it's growing the fastest when we're at half our carrying capacity. So that would be true for when p is equal to 6. Okay, now, then they switch gears on us, and they give us a different population modeled by a separable differential equation. So notice that we didn't actually have to do any integration or work with the actual logistic differential equation. I think for the most part they realize that that's going to take people a long time. So instead we are given a separable differential equation to work with, and they want us to find y of t if y naught is equal to 3. So to do this, we need to remember our steps for a separable differential equation, which are separate, integrate, don't forget your c. So we're going to separate our variables. When I do that, I'm going to end up with dy, I'm going to end up with 1 over y dy is equal to 1/5 times 1 minus t over 12 dt. I'm going to integrate both sides. That's going to give me the natural log of the absolute value of y is equal to 1/5 times t minus t squared over 24 plus c. Oftentimes it's a good idea to go ahead and find our c, go ahead and get those points. I've done the separation, I've done the integration, I did not forget my c. Let's go ahead and get the point for using the initial condition to find c. So I'm going to put in 0 for time, and I'm going to put in 3 for y. And that's going to give me that the natural log of 3 is equal to 1/5 times 0 minus 0 plus c. So c is the natural log of 3. Now that I know that, I can go ahead and edit my equation here that I've been working on. Natural log of the absolute value of y is equal to 1/5 t minus t squared over 24 plus the natural log of 3. I left the absolute value on there for a very good reason. Now I get to e everything up. This gives me the absolute value of y is equal to e to the 1/5 times t minus t squared over 24 plus the natural log of 3. And I have to determine whether or not I need the positive or the negative thing. I'm looking that my populations are always positive. My populations are never don't appear to be negative. The initial condition they gave me is 0 and 3. To get that, I need the positive part of this. So my equation is going to be y of t is equal to, and I could do simplification here, but I'm not going to because I don't want to make a mistake. And right now they haven't asked me to use this thing. They are going to ask me to use it in part D, but in the part C section, right, I would not simplify this thing other than to write it over again now with out the absolute value. So e to the 1/5 t minus t squared over 24 plus the natural log of 3. All right, in part D, they want me to find the limit as t approaches infinity. And I actually do recommend doing a little bit of simplification here. I recommend rewriting this part, so I'm going to rewrite that whole thing. Y of t is equal to e to the 1/5 t minus t squared over 24. I'm going to rewrite that plus as an e to the natural log of 3, so that you can then see that this is 3e to the 1/5 t minus t squared over 120 if I distribute my 1/5. So that's my equation that I want to take the limit of. So the limit as t approaches infinity of y of t. When I think about this, what's going to happen here? As my t's get really, really large, I'm going to end up with a negative number. See, this 1/5 t and this negative t squared, the negative t squared is going to end up being a lot larger than my t. So that means I'm going to end up with a negative exponent on an e, which means the e will now end up being in the denominator. And so this thing is going to be getting really, really large in the denominator now. And as this thing gets larger and larger and larger in the denominator, I'll end up with basically 3 over very large. And if I'm 3 over very large, that limit's going to become 0. That's what I'm going to get really, really close to. I'm going to get very, very, very close to the number 0. So that is the limit as this thing goes to infinity. All right, so let's see how they scored this thing. They gave you 2 points in part A, one for each answer, one for saying that at the initial condition 0, 3 that you got 12, and one for saying the initial condition being 0, 20 you get 12. That's just, again, knowing those facts, right, for logistic growth. Down here in the next one, when is it growing the fastest? Well, we said that was growing the fastest at half the carrying capacity, so we got 3 points for our knowledge of logistic functions, which is pretty great. Then we got 5 points for properly separating the variables, taking the antiderivatives, remembering your constant of integration, using your initial condition, and solving for y. We did all of those things in part C, so we get 5 points there, so we're up to 8 out of the 9 points. And then the last point, taking that limit that I imagine a lot of people made mistakes on because it was e to some stuff and they didn't think about the fact that that minus in there would mean that we'd have end up with a negative exponent as the things get large. Okay, that's the 2004 exam, so hope you all feel good about that one. Now let's look at the 2006 exam questions. This is from Form B. It's question number 5. And in this one, we are given a function. We're given some initial condition. This is initial condition 4(1). And here's its differential equation. This differential equation, again, separable. I can separate the y's and the x's pretty easily. Then I have another function, g, right? And with g, we were going to have its logistic difference. It is a logistic differential equation. So again, there it is. And to find this y equals f of x, again, we're going to use our separable differential equation strategies. So here we go. Part A. If I have dy dx is equal to 2y times 3 minus x, I like to go ahead, well, we'll separate. So 1 over y dy is equal to 2 times 3 minus x dx. I like to leave the 2 on the right-hand side. I just don't want to forget to handle it properly when I'm integrating. So I typically try to leave any constants on the right-hand side. Then I'm going to integrate both sides. So we're going to integrate. When we integrate, we get the natural log of the absolute value of y is equal to 2 times 3x minus x squared over 2 plus c. I'm going to use my initial condition to find out my c. I'll put in the point 4(1). So when I put in 4(1), I get the natural log of 1 is equal to 3 times 12 minus 16 divided by 2, or 8, plus c. Natural log of 1 is 0. So I end up with 12 minus 8, which is 4 times 3, which is 12, plus c. So c is negative 12. This tells me that my equation is, I have the natural log of the absolute value of y is equal to, I'm going to go ahead and multiply this 3 through, 9x minus 3 halves x squared minus 12. Now I'm going to exponentiate both sides, again making sure I pay very close attention to my initial condition. because my initial condition has a positive y, when I do this, I will end up with y equaling the positive e. If it had been negative, I'd need a negative on the front of the e. So 9x minus 3 halves x squared minus 12. Okay, there we did it. That is part A. Probably worth a ton of points. Let's talk about part B. So given that initial condition of 4, 1, and I want to find the limit of the function g. So what I need to know here is, it's like what I'm looking for in this function g is what is the carrying capacity here? Because the carrying capacity is going to be what the limit of this function is. When I'm looking at it, I think that is going to be 3, right? Because this is in that form of dy dx in this case is equal to ky times L minus y. So L is 3. So when I take my limit as x goes to infinity of g of x, I should end up with 3. When I take the limit as x approaches infinity of g prime of x, though, what should that be? Well, let's think about it. What is the shape of a logistic curve? Again, here it's coming in nice and, let me see where you can see it, nice and flat. Then it starts to go up through the exponential part, and then eventually it flattens out, right? And it flattens out. So what's the slope as this thing goes way out? Well, it's a slope of 0, or that's what it'll be approaching. All right, so part C. For what value of y does the graph of g have a point of inflection? Ooh, very good question. Find the slope of the graph g at that point of inflection. Look at this very important part. It's not necessary to solve for g of x. They're like, don't actually solve the function unless you have to. So when are we going to have a point of inflection? Well, we have a point of inflection when we change from this exponential part to the logistic part of the curve, or the log part of the curve. So when we flip there, that's at the place where we were growing the fastest, right? We were increasing our rate was increasing, and then we start decreasing. It's that point where we go from being concave up, our rates are increasing, to being concave down, our rates are decreasing. So that's at that point that we've talked about before as the point where we're at half of our carrying capacity. Our carrying capacity we determined earlier was 3, so we have a point of inflection when y is equal to half of that. Then they said find the slope of g at that point of inflection. Well, geez, if only I had some sort of equation that I could use to find slope given y values. Oh wait, they gave me one. It's right there. So I'm going to use this thing, dy dx is 2y times 3 minus y. So I'm going to rewrite this equation down here. Dy dx is equal to, I think it was 2y times 3 minus y. I want to put in, so so dy dx when y is equal to 3 halves is equal to 2 times 3 halves times 3 minus 3 halves. That's all I really have to do, guys. I mean, I can leave it just like that. I could simplify this if I wanted to. I could say it's 3 times 3 halves, or 9 halves. So I could get that if I wanted to, but I don't have to. All right? Right. Remember, we don't have to simplify things. This is PC calculus. So let's look at the rubric. Let's see how they scored this thing. 5 points again for our separation of variables, 1 for separating, 1 for getting the antiderivatives, 1 for getting our constant, 1 for getting using our initial condition correctly, and 1 for getting the solution. Oh, I must have made a mistake in there because I got negative 12, so I must not be able to do basic arithmetic. Let's find out what terrible arithmetic I did. Oh my gosh, I already see it. I'm insane. Alright guys, well, your math teacher is a little insane. I miscopied. I had the number 2 here, and then I switched it to a 3. Likely because of no real reason. So, it should have been 4 times 2, which is 8. And then that would have all been 8, so I apologize for that. Whoops! So that would have cost me the not the initial condition point, because I did use the initial condition. My, my my problem was getting the full solution. So what I would have gotten was 4 out of the 5 here. I would have gotten this limit. We did find the limit correctly here, so check there. I did find that it was 0, check there. I found out that this was going to happen when y was equal to 3 halves, and I found that that was 9 halves. So I would have ended up with 8 out of 9 on this problem. Because I made an arithmetic error. That, by the way, guys, is why I plug in that initial condition early. It also keeps me from making a mistake in 2 different ways, right? If, let's say, that I had made a mistake in solving the thing, and my problem was when I was solving for y. If I tried to solve for y and then plug in my initial condition, I might have made 2 mistakes, because I might have solved for y incorrectly, and then had the wrong thing to put the initial condition into and possibly miss 2 points. So we don't want to do that. And that's why I put in my initial condition the moment that I have integrated. All right, guys, hopefully this is a pretty good introduction on logistic growth. I hope this kind of gives you some idea of where we are on that. Your assignment has been posted up in our Google Classroom, so I'm sure you guys can get on that. And if there's something you guys need or something wasn't clear, please make sure to let me know. Go ahead and comment to me directly here, or you can comment on our Google Classroom. You can send me an email. I'd be happy to help however I can. Y'all stay safe, and I'll see you all soon.